The purpose of this lab is to model and predict the motion of the world's largest rope swing using Newton's second law. The speed of the jumper was calculated along 2 points in the trajectory, along with the spring constant and the stretch of the rope. The results show a difference in the numbers calculated and the numbers predicted by the Python model. The difference can be attributed to not including the free fall in the model predictions, along with not including air resistance. The speed at the bottom of the swing was calculated using the energy principle, where the final energy equals the initial energy. The energies included in this system would be the kinetic energy and the gravitational potential energy. Setting the changes in both equal to each other and realizing the initial kinetic energy is 0 because of an initial velocity of 0, then we can solve for the velocity at the bottom of the spring. To include the free fall, we would use the same procedure, but realize the final height used in the calculations would be 30 feet as opposed to the 10 feet from before. The tension at the bottom of the rope can then be calculated now that you know the final velocity. Using the idea that F net equals the sum of all forces, we see that the forces acting on the point particle system are made up of the tension of the rope along with the force of gravity acting in the opposite direction. Since the ideal system can be considered centripetal motion, we can set the sum of the forces equal to mass times velocity squared divided by the length of the rope to get our tension at the bottom of the rope. To calculate the velocity of the point particle system at another point, we choose the point of free fall, in which we have already calculated the velocity. To find the angle of the point of the free fall, we use the inverse cosine of the lengths of the rope and the height from the top to get an angle of 29.92 degrees. Using this, we can again use the idea that F net equals mass times velocity squared divided by r plus the force of gravity to determine the force of the tension. The force of gravity in this case is now only partial the total force and can be equal to weight times gravitational constant times cosine of 30 degrees. To determine the spring constant, we need to set up two equations. The first using the idea that F net is equal to the force of the spring minus the force of gravity. Using this first equation, we can solve for the final kinetic energy. Leaving that equation alone, we can also use the energy principle to determine the final kinetic energy. Using the idea that the maximum stretch allowed is 10% of the rope's length, we set that equal to the stretch of the spring at the bottom. Therefore, we now have two equations that allow us to solve for the spring constant. Now we can solve for the speed at the bottom of the real system, including the spring constant, which shows only slight variance from our ideal system. Finally, solve for the real stretch at 30 degrees, the height of the free fall. The model of this system was made to be in 3 dimensions, as the jumpers in the real video didn't just jump straight down and instead moved in 3 directions. The model also differs from the calculations in 2 ways. The model does not take into account air resistance, which would slow down the predicted velocity. It also doesn't take into account the free fall, which would accelerate the jumper even more. It can be seen from the model that both the force of the tension and the velocity reach their maximum at the very, very bottom of the swing. You can see that this is represented by the arrows and their magnitude being the largest at the very bottom. Hitting its maximum right here.